RAGs in production can be quite expensive, so let's try and motivate that with a very simple example. So consider a GPT-4 API call, and let's say that it can cost anywhere between $30 for every 1 million token that it generates. And you have 10k incoming requests a day. And the average token that is generated is about 1000 for each response. This means that it can take up to $300 just to maintain your service for a day, and it can go up to $9,000 for a month. Pretty expensive, right? So this is one of the fundamental challenges of getting a RAG system in production, where you will see your API exploited to the point that it can pile up massive amount of money and cost just to maintain it, even for a single day. So your next best bet would be using an open source model, but an open source model also comes with its own limitations, high latency. So let's think about this for a minute, right? Let's say you have a very small Llama 7B LLM deployed in a subpar VM with a simple fast API backend, which can handle at most 10 users concurrently. And let's say that you have 100 new requests coming in at the very same time. So what this essentially means is, while your first 10 users are being served, your last 90 users are simply waiting for work to be done. They're just sitting there idle, and this leads to massive latency and a very bad user experience. So this is where semantic caching can greatly help and aid in preventing those two fundamental issues. And what semantic caching essentially says is, you will try and store your previously answered responses and questions in a semantic cache, and every time a new query comes in, you will first look it up at your cache. And let's say that you have a cache found. And when I mean a cache found, it means that you take your new question and you cycle through your old previously answered questions, and let's say that you have a threshold defined, a Euclidean threshold, that anything below zero point 0.5, they're similar, and I'm happy with that similarity. So you will look through that, and you will calculate similarity between your old responses and your new responses, and anytime these embeddings are similar or a match is found that is below the threshold of zero point 0.5, which is set by us, you're happy with that question, and you say that, you know what, it makes sense for me to cycle that response, so let me not use another API call, and let me take that response and give it to the user. So that is essentially what this flow diagram is saying. So you have, from left to right, you have your documents that are ingested in a vector database, and you have a very small cache that is sitting in the middle. And every time your new query comes in from the top, you look it up at a semantic cache, and when your cache is found, you will bypass your LLM call, and you will directly return your previously cached response to the user. If your cache is not found, you will have to make another LLM call, and then you will be passing it back to the user. So now this solves the two major fundamental issues that we previously faced. One is your API cost. There's no API at all. You're just using a cache. Number two, there is yet again no latency. There's probably a very small latency because of the lookup that you have to do in your cache, but it's not as significant as previously, where you have 90 users just sitting there waiting for your previous guys to generate 1 million tokens, or anything. But this comes with a very small trade-off, that you will need some additional store or disk space to store your semantic cache. Let's try and understand the overall code structure. Now with how my directory is laid out, nothing special here. We just have a main caching.py, and we'll look at the other directories consecutively. So I'll just close my navigator for now. So starting with imports, we have very simple imports. We'll be using ChromaDB as a vector store. We're also using 5cs. I'll just show you why we need 5cs for. And the data sets, for loading our data sets, and Logiro is actually my favorite logging tool, and sentence transformer for the encoders. So first we're loading the data set from a metcall, and we're using the train split, and I'll just quickly show you what the data set has. It has a q type, question and answer. So q type is telling what sort of question type it is, and question is what is the specific medical question, and answer is the answer to it. So you have basically three fields. So first I'm converting to a pandas data frame, and I'm extracting out the index. We need this index later on, and I'll just show you how. And right now I'm using only 100 rows, but originally I think it has about 16k rows, and this is a very small sample that I'm just printing, right? And we're using ChromaDB to create a persistent client on the disk, and this is my path. So that's the path that I gave here. So I'm telling that store it on my disk at this path, and my collection name is meddb. And this if else block, all it's saying is, if my collection is already existing and if it has some rows inserted in it, do not create the collection, and I will simply just retrieve the collection that already exists. If it does not exist, go ahead and insert stuff into it, right? What is being inserted? The first part is IDs, the unique IDs. You need that for a Chroma vector database. And metadatas. So metadatas was the Q type that we saw in the data set. So you can see that loop running here for in my subset data. For every topic, convert it to a list and store it in sort of a JSON dictionary type of format in the original documents, converting into a list and storing my answers basically. So that is what is stored in this ChromaDB collection. Query database will simply query for your top n values. So you will get our question in, and we will return the top n results. So this part is our cache. This is one part of the cache where we are using a 5Cs index with 760, and we're storing 768 vector dimension embeddings, and we're using the index flat L2 index of 5Cs, and there's a reason why we use that, which I'll come to later on. And we're also initializing our encoder. So 5Cs will exclusively be used for only storing our vectors, and we'll see how we're storing the other parts, right? And retrieving cache, all it does is, if the cache is already there, if a JSON cache is already there, give it, or else we create our new cache. And in this JSON cache is where we store our questions, embeddings, answers, and the response text. And then we finally just return the cache. Storing cache, just store it, just JSON dump it and store it on a disk. So semantic cache is the main crux of the problem, and where we define a name for the cache or the JSON file, and we have a predefined threshold. In my case, it's 0.35. So 5Cs by default uses Euclidean distance, and you can use cosine as well, but it is a little difficult to set it up, or it is a little time consuming. So I just use the default Euclidean threshold. And in terms of Euclidean threshold, the smaller the better. So you might want to keep it as small as possible, and distance of 0 means you have an exact match. So you initialize all of those, retrieving the cache. If it's present, it just retrieves it. If it's not present, then create one, and then you start logging the time. So ask is saying, when my new question from the user comes in, I will first create an embedding out of it, and then I will search it across the index. And when you search it, what it returns is, it returns two things: the distance of the nearest vector and the indices. And if your distance is sort of less than 0, it means, like, if it goes in the negatives, it does not exist, so you can safely ignore them. So what this if loop is saying, that if it is greater than 0, okay, there is a match. And then you'll check the threshold, that if the match is there, and if my index value is also greater than 0, which means it is present in my 5C's index, and if my threshold, if my defined distance is lesser than my Euclidean threshold, okay, that's a fine. That is what I'm going to retrieve from my cache and give it to the user. So I'm just logging those details. Retrieved from cache, found in cache, what is the row ID, what is the response text, and which row it is present from. And that is essentially what you're doing here. And then we just return our answer or the response text. If it is not present, we'll just query the database. From the database, we'll get our best match, and then give out the response. And since this is not present in the cache, we'll all we'll add our new response and new questions and all of those back into our cache, and then we log out the basic details. And along with adding to the JSON cache, we also have to make sure we add it into our 5Cs index as well. So that's what happens here, and we store cache, that is write it back into our disk, and then you log the time for how long this took. And you have a very simple exception log. It's nice to have exceptions, right? So this class semantic was the crux of the whole code, and let's see how we can try and use it. So we initialize our class, and this is the name I'm giving for it, and we're asking two questions basically. Cache.ask what vaccine for La Crosse encephalitis virus. I'm not sure what that is, but yeah. And then the second question is also pretty close by, right? So it says list down vaccines and precautions against La Crosse encephalitis virus. So ideally, since our second question is kind of similar to first one, you should expect it that it retrieves from the cache. But let's see what happens, right? So now I have a virtual environment, so I'll just initialize it first. So .n/script/activate. So it has activated, and now let's run our code, python caching.py, and let's try and see what happens. Just keep questions intact so it's easier to see. So this is a sample of the data set that just got printed, and in my case, since my collection already exists, I already have it in my vector database, so it skips through it. And you can see that for the first question it was retrieved from the database, so no caching was used, and this was the response for it. And it took about 0.75 seconds, fairly quick, but you should also think that our vector database is quite small, so you can expect the answers to come fairly quick. And the second one, you can see that it was actually pulled out from the cache, and it had a threshold of 0.30, but this was the threshold that we defined 0.35, so will try and retrieve anything below 0.35. So that's the reason it was retrieved, and we're using the same previous answer. If you read through the both of these answers, both of them are very identical, but the main point is, look at the time that it took. It only took 0.046. That's almost a factor of about 80 to 90 times faster, I believe. So this is how you can try and implement semantic caching. There's also way more advanced stuff that I think Redis has its own caching mechanism as well. I think that's pretty cool, and you should check that as well. And there's also something called GPT cache that's also pretty nice. I think it has a couple of integration with LangChain. That's also another amazing option. But this is a very simple way to get started with cache, and I recommend you guys to try it and see how it goes for you, right? So let me know in the comments if you have any doubts, and I'll see you in the next video. Bye bye.